yeah, we are very happy to have Professor Shuchi Chawla from UT Austin today with us. Shuchi is interested in information algorithms, online algorithms, AGT. She has written a lot of like early pioneering influential papers in correlation clustering, multi-parameter mechanism design, approximation algorithms, orienteering, and TSP. She's received numerous awards for her research, NSF Career Award, Sloan Fellowship, and a lot of awards from UW-Madison for teaching and research, including Chancellor's Teaching Innovation Award and Provost Career Award. So today she's going to talk about a multidimensional online contention resolution scheme. And Shuchi also advised me for PhD.
Thanks, Balu. It's really fun to come back here after many years. I'm happy that EC presented the opportunity to do so. Okay, so this work is joint work with my students, Dimitris, Trung, Z, Greg, and Rojan. And it's actually something we started, or I started working on when my ex-student Yifeng Teng, who is not here right now, this was part of his PhD thesis. So you'll see a little bit of that in the talk. Okay, so I'll start with the really quick motivation. I don't think this crowd really needs too much motivation for this question, but we're looking at the classical economic problem of revenue maximization, where there's a seller having with many items to sell. There are multiple buyers with combinatorial valuations for these items. These buyers are drawn from some population, so we're going to assume throughout that there's some underlying distribution from which the valuation of each buyer is drawn. And as I said, these buyers are combinatorial, so they assign some value to every possible subset of items they can purchase. And what is a selling mechanism? It's going to take all of these value functions. It's going to determine what to give to every person and what prices to charge them. And the standard setting is that every buyer individually wants to maximize the value they get minus the payment they make. And the seller wants to maximize their revenue subject to incentive compatibility. And I won't define everything very formally. Some of the details are not pertinent for this talk, so we'll just leave it at that. But let me just say that the optimal solutions to this mechanism design problem turn out to be quite complex and unwieldy. There's Feng. He didn't miss anything. So in particular, even if you just have a single buyer, these mechanisms can look like menus that sell many different kinds of subsets of items, but also lotteries over subsets of items or random allocations. And furthermore, when you have multiple buyers in the system, then buyers exert externality upon each other. So now you have to deal with questions of, should I allocate this item to buyer one or buyer two? From the perspective of any single buyer, what they're going to get and how much they're going to pay can be some complicated function of the other person's valuation, and so it can be inscrutable to the buyer what's going on in the system. And so, the big a common theme in this area of algorithms for mechanism design has been to try to figure out, are there simple mechanisms, where simple is defined appropriately, that will approximate the optimal one? So that's the question we want to address. And cutting to the chase, the answer, one answer we'll give in this talk is that under mild assumptions, and if you pick the right benchmark, we can give positive answers to this question. And so to be more specific, the simple mechanism we will talk about is sequential item pricing. So let me describe what that is. So we're going to interact with buyers one at a time. And every time a buyer appears, we're going to look at the set of items that we haven't allocated so far. So there is some remaining set of items. We're going to offer an item pricing over the set. So every item has a fixed price associated with it. And the buyer can select any subset of items to purchase and pays the sum of the prices in that subset for those items. And then we move on to the next buyer and the next buyer and so on. So that's sequential item pricing. And this is the simple mechanism that we'll come up with. The benchmark we'll approximate, and this is a bit of a mouthful. It's going to be the ex ante by many benchmark, and I'll tell you in a little bit what is this benchmark and why this benchmark, or why is this what we're comparing against. And then the results will look like the following. So depending on what kinds of valuations the buyers can have, we'll get some approximation factors to these benchmarks, and I'll define these terms as well. But the important thing I want you to notice is that while we'll make assumptions, we'll restrict the class of valuations, we won't need any further assumptions to make here. What are the kinds of distributions? Are they small support distributions, large support distributions? Are the values bounded? We're not going to need any of those assumptions to be able to achieve these approximations. The approximations will be independent of the number of buyers in the system. They'll only depend on the number of items, and in particular, the number of distinct items. So you could have multiple copies of the same item, and that will not affect the approximation. Okay, so that's kind of the upshot before having defined all of the terms. But furthermore, I just want to say that we'll further simplify the benchmark at some loss in approximation, and the actual benchmark I'll focus on for the most of this talk is what's called the ex ante item pricing revenue, and I'll define that as well. And then, as I said, really the approximation factors will depend on the number of distinct items.
Beyond subadditive, there is no hope.
Yes, so I'll mention some lower bounds and such. Yeah. Okay, so I'll start by talking about the context, what else is known about revenue maximization and why the benchmark, and then I'll introduce our framework for coming up with these results. It's a new kind of online contention resolution scheme that leads to these approximations. Okay, so as I said, a dominant theme within algorithmic mechanism design has been the simplicity versus optimality kind of results, and simplicity comes in many forms. These are some of the kinds of mechanisms that have been looked at in this literature, and we're basically asking, when are the revenue gaps between these simple mechanisms and the optimal ones small? And there's a large literature at this point on these topics, and some of the works are by people in the room, and I certainly cannot hope to have an exhaustive list here, but the upshot is that this gap is often known to be small in many settings, but the bad news is that the typical assumption that all of these results need to make is that the value distributions have this product form. So, if you have a buyer that's interested in two items and let's say has additive values of the over the two items, the results that are known in this context would assume that the values of the two items are independent for the buyer. So if there's some correlation between them, then there's not much we can do. There's some results under correlated settings, but these tend to be fairly sparse. But if you don't make any sort of independence assumption, then it turns out that, in fact, you can find instances of this problem where this ratio between the optimal revenue and the revenue of a simple mechanism, again, simple within quotes, can be completely unbounded. Unbounded in terms of number of items, number of agents. Here, this is even just for one buyer and two items. But of course, this corresponds to some distribution that has unbounded support, unbounded range of values, and that's where this arises from. Okay. Any questions so far? Okay. So the question we wanted to ask is, can we say anything about the revenue maximization problem in the absence of any independence or close to independence type of assumption on the value distributions? What would that theory look like? And this is an agenda we got started with Yifeng's PhD thesis. And the one particular answer we came up with is you can make progress on these questions if you look at a different benchmark to compare against. So what is this benchmark? Very, very briefly, the unbounded gap result I showed you, all results of this form actually have mechanisms that have super additive pricing. So, the price of a bundle of bananas and oranges will be strictly larger than the price of the bananas alone plus the price of the orange alone. And this can be a strange thing to observe in many markets. So we asked, well, what if you impose a kind of subadditivity over the mechanism? And one sort of motivation for doing that is to say, well, the buyer can purchase multi-sets of options from a menu in the mechanism, and that naturally gives a rise to subadditive pricing. And so it turns out that if we optimize over these so-called by many mechanisms, then these can be approximated by item pricing to within a factor that's logarithmic in the number of items. And this holds for any value distribution over m items. And furthermore, this is tight. So no mechanisms can beat, no simple mechanisms can beat this logarithmic factor. And so I want to emphasize here that by many mechanisms are a significant restriction over arbitrary mechanisms, in the sense that I already told you that, this opt to simple mechanism gap can be unbounded, whereas this gap is always bounded. And so necessarily there are instances where these will be far, far worse than the optimum. But nevertheless, in many markets, this kind of subadditivity assumption is a natural one to impose. And then you can say that, this is a reasonable benchmark to compare against. Yeah.
This is for a single buyer.
This is for a single buyer. You have a single buyer, but many items. And so that's a great cue. So now we'll ask about many buyers, right? And so then the question is, what happens in multi-buyer settings? And we looked at this last year, and it turns out there are many ways that you can extend this by many definition to multiple buyers. And I'll skip over, the possible approaches there. And instead, I'll introduce to you an ex-ante relaxation that captures many of those extensions in one go and gives us a convenient upper bound on the revenue that any of those extensions can achieve in a multi-buyer setting. So what is an ex-ante relaxation? This is a concept that was introduced several years back by Saeed Alay. And it's a way of taking a multi-buyer problem and saying, well, the externalities the buyers are imposing on each other are too complicated. Let's simplify them by relaxing our supply constraint slightly. So what we do is, so what is a supply constraint? Something of the form, no matter how buyers' values are instantiated, we're going to sell each item at most once because we have one copy of this item. And we're going to relax that to say that in expectation, we're going to sell this item at most once. So sometimes we might over-allocate, sometimes we might under-allocate, but in expectation, we're only going to sell this item once. And since we're talking about expectations, now we can ask, what is the probability I sell the item to the first person, and then the second person, and the third person, and so on. And once those probabilities are fixed, now each buyer's problem becomes completely disjoint from the others. And so it's a way of factoring this multi-buyer setting into its single buyer constituents. Okay, so to be precise, the ex-ante relaxation is going to come up with, so again, we have a set of items, we have many buyers, and ultimately we want to allocate every item to at most one person. But we're going to come up with different mechanisms for different buyers. So M of I is a mechanism for buyer I. And we're just going to impose the constraint that the sum over the probabilities that some item J is allocated to buyer I is at most 1. And we're going to, subject to this constraint, we're going to find this collection of mechanisms that maximizes the revenue. And in our setting, furthermore, we're going to impose the constraint that each of these are by many mechanisms. And we put all of this together. This gives us this ex ante by many benchmark. Okay. And so formally, we'll capture these probabilities through variables that I'll denote by xij. So xij is the intended probability of allocating item j to buyer I. These are these ex ante supply constraints. And then we'll say that a mechanism satisfies a given supply constraint if over the value distribution, the probability the item is sold is at most this supply constraint. And I can, optimize over the class of, optimize for revenue over the class of all mechanisms that satisfy the supply constraint. And then what is this ex ante objective? It's maximizing over all possible ways of taking the entire supply, partitioning it across agents, and then optimizing for by many revenue over each agent independently. Does the benchmark make sense to everyone?
So how do you define the by many mechanism for multiple buyers? Or is it
Here I'm avoiding defining it for multiple buyers by first factoring the problem into single buyer problems. And for a single buyer now, I can define this optimal by many revenue subject to a supply constraint by saying, let me look at all possible by many mechanisms that will satisfy this supply constraint. And over those, I'll take the one with the most revenue. Okay, so now each of these is a single buyer problem. Like each of these in here is a single buyer problem.
So in the box, like the mechanism M that you define here.
This is a single buyer mechanism.
This is a single buyer mechanism.
Yeah. So here I'm talking about a single buyer problem. Yeah. And I'm happy to discuss offline a little bit about, how you might define a by many mechanism for multiple buyers, but I'm largely skipping that in this talk to get to the OCRS stuff. But happy to have that conversation offline. You have questions?
Is there any known results about the gap between the optimal mechanisms with and without the relaxation?
With and without the ex ante relaxation. So that's a great question. So I think you're asking, how much larger is this relative to the, the ex post feasible problem? And I don't know, but ultimately what we will do is, approximate this quantity using a mechanism that is ex post feasible and by many. And so that'll give us an upper bound on that gap. And it will be those factors I showed you before, and I'll show you again.
One slightly related stream of work where this gap shows up is in profit inequalities, where there is a 1 minus 1 over E
Correct. Yes,
because of
you.
ex ante feasibility.
Yes.
But the 1 minus 1 over E for free order profits kept on getting improved. Like right now it's at 0.7258, for example, close to the 0.745 Hill and Kurtz bound. That's because of not comparing to the ex ante feasible. If you compare it to this, 1 minus 1 over E is the best for the pre-order profit inequalities block.
So the value of the benchmark is, again, in terms of whether it lets us prove interesting results, because otherwise, we might as well use opt, but against the optimal revenue, we know we cannot have any finite approximation bounds. So again, we showed in this paper from last year that just like for the single item setting, now if I look at this ex ante constrained version of the by many revenue for a single buyer, then no matter what my ex ante supply constraint is, I can approximate this using item pricing revenue within a factor of log m. M again is the number of items. And this quantity here, this is really the same problem that I defined here, but optimizing over item pricing. So again, I have this ex ante constraint y, and we're asking of all the possible item pricings I could offer to this buyer, where the probabilities of allocation will be no more than these yj's that are given. Of all of those y feasible item pricings, what is the one that maximizes revenue? And that's what I mean by this item pricing revenue quantity here. So again, we can show this logarithmic approximation, and this is typed. Okay. And just like we defined the ex ante by many optimum here as, partitioning into the optimal x's across buyers and then optimizing separately for each buyer over by many mechanisms, we can do the same for item pricing, and this gives us an ex ante item pricing optimum. And so what I just told you is that the ex ante item pricing optimum is a logarithmic approximation to the ex ante by many optimum. And so this is really the objective now that we're left with at this logarithmic loss. And this is the objective we'll focus on for the rest of the talk.
This is for subadditive.
No, this is for arbitrary distributions over arbitrary values. So this holds for any possible values in any possible.
That was because you're comparing against ex ante IP. Is that the reason? Or item pricing? Or so this is many buyers, right?
Many buyers, yes.
I
Correct.
thought you said you can't go beyond your.
Oh, yeah. So once we try to approximate this objective,
yeah.
then we'll now have to restrict values to get good approximation factors, and I'll come to that. Yeah, yeah. But this result is for any distributions over any values.
While comparing against not the item pricing, but the optimal mechanism, by many mechanism, the BIC versus DSIC, does it come into picture because of all this correlation, or doesn't matter?
So the correlation is across items, not between.
Between buyers, there's always
buyers
independence.
are still independent, correct? So we're not
Because
talking
otherwise
about.
BIC will become very messy.
Yes, yeah. So we're not talking about correlations across buyers. That's a slightly different context. Yeah. Okay. So let's just at this point look at an example just to make everything a little bit concrete. Just want to show you through an example, what does this ex ante item pricing benchmark look like, and why is it different from a sequential item pricing? So here I have two buyers and two items. This first buyer is what we'd call a unit demand buyer. They're only interested in buying the one item. So this buyer with probability 1/2 has a value of 1 for the banana and doesn't want the orange at all. With probability 1/2 has a value of $3 for the orange, doesn't want the banana at all. This buyer is an additive, well, actually not an additive buyer. They are in fact even not even subadditive for the sake of the example. So with 1/2 probability, they want both the banana and the orange for $5, and they're not going to want anything less. And with probability 1/2, they just have a 0 value. So here's an ex ante optimal item pricing for these buyers. Basically, it manages to extract all of the value of these buyers as revenue. So what it does is it offers to the first buyer, it offers the bananas for $1, orange for $3, and depending on which one, which value function is instantiated, Alice purchases this or this. And notice that the allocation probabilities are 1/2 and 1/2, with half probability Alice buys a banana, half probability buys the orange. And then simultaneously we can offer to this buyer, Bob, any pricing where we charge no more than $5 for the pair of the items. And with 1/2 probability, this buyer is going to purchase the pair because they can afford the prices. With 1/2 probability, they don't purchase anything. And so again, the allocation probabilities for the individual items are 1/2 and 1/2. And so for each item, the expected allocation is just 1. And so this is good. Our ex-ante supply constraint is met. So this is a ex-ante feasible pricing. But of course, it's not ex-post feasible because, if we sell any item to Alice, we cannot sell the pair to Bob. We can't do that simultaneously. And so in particular, if we just try to offer this particular pricing in sequence, then, we get a revenue of $2 in expectation from Alice, and now we can't get anything from Bob at all. Alternately, we could skip Alice altogether, and then we could sell the pair to Bob for $5 when this top value function is instantiated, and we'd get $2.50 in expectation. That's okay, still not quite at this level. So that gives you a sense of why the ex-ante supply constraint is quite a bit weaker than the ex-post supply constraint. And it turns out that for this particular example, there's a sequential pricing that can do slightly better. What it does is it only tries to sell the orange to Alice. And with 50% probability, we sell this orange, we make $3 and nothing else. And with 50% probability, we didn't sell to Alice, and then we go to Bob. And with a further 50% probability, Bob instantiates the stop value function, and we get $5 for selling both the items to Bob. So slightly better than the $2.50.
Reverse order, no? For Bob, you can get $2.50. And at the 50% probability, and another 50% of the quarter, you can get 3, which is 3/4, and you get 3.25.
Good. So you could do even better if you switch the order, right? So this is not the optimal sequential pricing if you switch the order. For this order, it does turn out to be optimal. But the question we're going to ask is, how close can this quantity get to this quantity here? That's what we're interested in. Okay. So any questions at this point? So for the rest of the talk, this is the question I'm going to focus on. We have this ex-ante item pricing benchmark, and we want to approximate it with a sequential item pricing in revenue. And we are not going to be selective about the ordering of buyers. So we'll think about the ordering as being given to us, and we'll ask, how well can we do for this ordering? Algorithmically, what is the best we can do? And our main result then is that for any given distributions over M items and N buyers, this gap between the ex-ante item pricing optimum and the sequential item pricing revenue is bounded by some factor that depends on the class of valuation functions the buyers have. So this is like our full table of results. I will focus in this talk on subadditive values because that's the most technically interesting result. So subadditive simply means that value of A plus value of B is greater than or equal to the value of the union. I think we all also know unit demand. I will briefly touch upon gross substitutes and XOS as we go through the arguments. But for up to gross substitutes, we can show that this gap is at most 2. And this is already tight because it generalizes the standard profit inequality. For subadditive values, we get a logarithmic factor gap here. And we also know that there's a square root of log m lower bound already for XOS values. So that gives a lower bound here. And I kind of suspect that this might be log m, so that this log m is tight, but we don't know that. But for general values, there's a polynomial lower bound on the gap between these two quantities. And that's sort of just because there's a kind of rounding involved in going from these ex ante supply constraints to ex post supply constraints. So it has nothing really to do with the revenue objective or with item pricing, but it's just sort of like the rounding gap for like a hypergraph matching type of problem. That's where this gap comes from. Yeah.
You know what's happening for submodular evaluation?
We don't. That is one of our open questions. It's submodular. I don't know.
Shouting.
Yes, I completely agree.
That's written.
Yes. So yeah, it could be constant. We have, I'll show you as we go through the results why XOS is not a constant, whereas in many settings, XOF also turns out to
Did
have.
you look at the special cases of submodular, like budget additive or coverage?
No, we didn't. So yeah, those are all interesting questions. Okay.
Sorry,
Yes.
one question about the benchmark. So this like the left hand side, like there's an TIP opt. So do you assume like each item is at most allocated once, right? The sum of xij's is at most one. So that's like in the benchmark. So I wonder if like, like suppose I know like the sum of these values are less than half, for example, so that like, you will have maybe like at least like half of probability when each of the buyers are coming, you have at least a constant probability of the, each item's available. Are you able to achieve like better or like,
So this is actually what our technique will be like, because we design an online contention resolution scheme, and that's kind of the way these go. So if you're asking about this log m, that'll stand despite having a constant probability of every item surviving to the end. Yeah. And I'll spend some time on explaining where that comes from. Yeah. Okay, so I'm going to go into the definition of an OCRS, and don't worry if you haven't seen this before, because you'll see a simple example. Okay, so what is an online contention resolution scheme? So these were first, developed in the context of approximation algorithms for like submodular optimization and such. They're a way of sort of rounding the relaxations in an online fashion. And I want to talk about this in the context of single dimensional profit inequality type problems or allocation type problems. So again, within our familiar framework, we have n buyers, but now let's say that we just have a single item to sell. And what are ex ante allocations in this setting? They're just the probability of allocating the item to this buyer. And so we have this constraint satisfied by the xi's. And this online rounding process, what it's going to do is it's going to go from buyer to buyer. And then when it reaches buyer I, it's going to ask, is this buyer already blocked? Meaning I've already allocated the item. So of course I can't do anything else. If so, the game ends, but if the buyer is unblocked, then I'm going to allocate to the buyer with some probability. And what do I want this probability to be? So I want this to reflect the xi's. So I want it to be comparable to the xi, but I don't want it to be too large because this is going to block future buyers, right? So the idea is that, so here's a simple 1/4 OCRS. That would be the first thing one might come up with. We'll do exactly what Ming-Fei described. We're going to allocate to every buyer if they're unblocked with probability xi over 2. Okay, so shave off a factor of 2 there. And now the implication is that, well, I had a total probability of 1 of allocating this item. If I remove, place this factor of 1/2 here, then I have a total probability of 1/2 at most of allocating the item through the entire process. And so when I reach buyer I, they are unblocked with probability at least 1/2. Okay, so I get that the probability that I is allocated is at least this 1/2 probability they're unblocked times the probability they're allocated given they're unblocked, so xi over 2, and that gives me this xi over 4. So the ex ante relaxation was allocating to this buyer with probability xi. I'm allocating with probability xi over 4. I'm a factor of 4 off in my probabilities. And for an objective like welfare or even revenue, because these objectives are concave objectives, this 1/4 here translates into a 1/4 approximation here. Okay, and to be very precise, for revenue, if I want to allocate to a buyer with probability xi, what I'm going to do is I'm going to set a price that is the value at the xith quantile, roughly speaking, for this buyer. And if I'm instead allocating with probability xi over 2, I'll pick the value at quantile xi over 2, and this is going to be larger than or no smaller than the value at quantile xi, the top xi quantiles. And so that's this concavity of revenue essentially. And so we get this 1/4 approximation to revenue. Okay. So that's how this sort of single dimensional online rounding goes. And really the key thing we used is, these allocation probabilities are comparable to xi, but not too much smaller. So what about the multidimensional version? We'll try to do something similar. So we have these ex ante constraints now, these variables xij that capture these ex ante probabilities. And again, we're going to go buyer to buyer, and we're going to find some allocations for each buyer over items that haven't been allocated so far, while maintaining these kind of allocation vectors. So we still want our allocation vectors to be about some constant times xi. That's what we want to try to do. Okay. And then maybe we'll say, we again appeal to the concavity of revenue. The ex ante relaxation was allocating with probabilities xi. We did alpha times xi. Surely we should get an alpha fraction of the revenue. That would be the hope here. Okay?
That's like scalar multiplied to a vector, right?
If it were exactly a scalar multiplied to a vector, it would be good. But otherwise, it doesn't quite work out this way. And that's sort of one challenge in doing this. And another thing to note is that we're not just talking about making arbitrary allocations to the buyers, but rather we said we wanted, some sort of simple mechanism like an item pricing. And so these are, allocations that are generated over the given value distribution by something like an item pricing. And so it really restricts us in what we can do here. We can't generate arbitrary allocation vectors, only those that arise from item pricings. So we refine the definition a little bit, and I'll go over this. And this is how we define the OCRS for revenue. So we think about what happens at iteration I when we're dealing with buyer I. We're given some value distribution. We're given some remaining set of items that have not been allocated previously to 1 through I minus 1. We have this ex ante constrained xi. We have some ex ante optimal pricing pi that satisfies this constraint. And this is what we're trying to compare against. And we want to construct some new pricing, I'll call it qi, over just these remaining items that has the following two properties. So first of all, we want to make sure we don't over allocate the items. So we'll say that the allocation of qi should be at most, let's say, 1/2 of xi. This is just in line with what we did in the single dimensional case. And we want the revenue of qi to be some fraction of the revenue of pi. Okay. This is what we want to do. Now, one thing that we should notice is that the pricing pi, which was this ex ante optimal thing, is actually allowed to allocate any of the items because it only satisfies the supply constraint in an ex ante fashion. Whereas QI is limited to selling this set Ri of items. So of course, if Ri is very tiny, then we can't hope to achieve this. So we need some kind of a condition on Ri. And that's what this is, hoping to establish for us through the process, right? And so the point I'm making is that in order to be able to prove, the existence of a QI with these properties, we need some precondition on Ri. And the precondition we'll choose is that every individual item is going to belong to the set Ri with some probability, again, precisely what Mingfei said. Right, and this property will actually hold by induction if I'm able to prove something like this. Okay, but I also want to just quickly point out that we're not saying anything about how different items, the containment of items in Ri is correlated across items. We're not saying everything is independently present in Ri with probability 1/2. Just if we look at the marginals, they're at least 1/2 for every item.
You cannot say that also, right? Because
Yeah, we cannot say anything about correlations, right? Okay. So this is our goal now. This is what I'll call an alpha OCRS for revenue for this purpose. So now we put this precondition on the set Ri and we ask, does such a pricing QI exist? Any questions about the definition? Okay, and so I already sort of argued for you that if we can prove this step, this iteration I, then this gives us an entire end-to-end argument for comparing the ex ante item pricing optimum with the sequential item pricing. Okay. So that's our goal. And I want to now run through an example that illustrates some of the challenges that come up. And in this example, we'll think of the menu of items as being the menu of choices if you go out for dinner. And here I'll say that this menu has a few tapas items that bring the buyer some small value if the buyer purchase. So the buyer's value is additive over these items. And then there are some main courses and the buyer is interested in one of these and the buyer will choose one or the other. So this is what would be an XOS type of valuation. You have, some different additive functions and you pick the best of those different choices. Okay. And in this example, so here the values of the tapas plates are 1 plus epsilon each, and the values of the main courses are a little bit larger. And it turns out that if we pick a price vector, which is 1 everywhere, and we had no other constraints, the buyer would basically pick all of these plates. The utility is this little gap between the values and the prices. And this blue block gives more utility to the buyer than any of these individual blocks. Okay? But if if we already sold one of these plates and now it's unavailable, now the buyer's utility drops because they can only select, the remaining plates. And now we set things up in such a way that the buyer is going to shift to buying a main course. And, of course, from the buyer's viewpoint, not much has changed. Their utility is still great. But from the seller's viewpoint, we were getting like a total revenue of K before from selling K plates. And now we're getting a revenue of 1 from selling 1 plate. Okay, so the revenue decreased by a lot. So if you think about this for a little while, there's one simple solution to this setting, which is, well, let's just lower all the prices and, that shifts the buyer's preferences back to this large set of items where now we get more discount the more plates you purchase. And so, the buyer will again buy this and we'll get a good fraction of the revenue. Right? let's change the example a little bit. So this time around, the values of the individual plates are quite a bit higher. And now I have more of the tapas plates unavailable. So even if I decrease the price on all the plates, the hit to the utility from these unavailable plates is large enough that the lowering of prices doesn't make up for the lost utility on part of the buyer. And so the buyer still shifts to purchasing one of these more valuable main courses. But here again, we can now ask, well, if each main course has such a high value, why don't I just increase the prices of those, price out the buyer on the small plates, and then they'll buy a large plate and I'll get good revenue. And that's works fine. Now I'll make the example more interesting and I'll say, well, I'm going to allow the buyer to have additive values over small chunks of the main courses, where, so the buyer now values up to L main courses at a value of some K over L each. So if I knew what this L was, then I would raise the prices appropriately to get good revenue on those plates. But if the L is chosen randomly by the buyer, then I don't quite know how to appropriately price. So again, the ex ante pricing is just fine because it's only going to sell the tapas plates that are all available to it, and that's like the safe thing to do here. But if some of the items are unavailable, then we cannot go with the safe choice. It doesn't bring enough utility to the buyer and enough revenue to the seller. But then, we have to price appropriately these main courses, and the value of those main courses is random, and so we can't extract enough revenue from them. Okay, so that's in effect what happens. And furthermore, in this example I ran through, the way I represented it pictorially, we're constantly, shifting the prices uniformly up or down. And you might ask, well, do it non-uniformly. But we can add more randomness to the buyer's value function and set things up in such a way that in the context of this example, it's not quite going to help to price items non-uniformly. Okay. Any questions? So what's happening essentially, at a very high level, is the key thing in this OCRS is that that the ex ante solution is allowed to sell everything to the buyer, but we must deal with the non-availability of some of the items. And that non-availability is going to make the buyer's preferences shift. And the preferences can shift in such a manner that even if we don't worry about the ex ante supply constraint, we didn't talk about that at all in the context of this example. Even if we don't worry about that, this non-availability is going to shift the buyer's preferences in such a manner that it could hurt the revenue we can achieve. So that's where this gap comes in. And we can in fact set up this example in such a manner that it provides a gap of precisely this logarithmic NM factor between what the ex ante solution can do and what any exposed solution can do for XOS valuations. Okay, so this answers partly your question. But I also want to mention here and tell you a definition of gross substitute valuations that are a subset of XOS valuations. By definition, these are valuation functions where if I fix a pricing and then I remove some, and then the buyer has some demand based on these prices, and now I remove some items and offer the rest at the same prices, the demand of the buyer, the demand set of the buyer, only increases in the sense that if I remove item J and they were purchasing item J prime, they still continue to purchase item J prime. And so the implication is that if we didn't worry about the ex ante supply constraint, just the non-availability of items does not hurt the revenue of the seller for gross substitute valuations. And this is where we have this factor of 2 for gross substitutes, and we have this factor of log m for XOS, and this is precisely where the difference between those two arises.
For gross substitutes, you just do like a single item. There is nothing else to do. You just lower the.
For gross substitutes, you can use the same pricing, but we still have to fix the issue of so the buyer can now can switch and buy extra items, and so we do have to worry about the ex ante supply constraint. But we'll be able to solve that problem with just a small constant factor loss.
The little o log m, is that cover integrality, or where does it come from? Log m.
The log m comes from basically embedding a kind of equal revenue distribution here on these prices. Yeah, and from how large the sets of items can be to support that. That's where it comes from. Okay. So let me tell you how we get the upper bound of log m here if we didn't have to worry about the ex ante supply constraint. So basically what we do is some combination of what I already showed you in the context of that example on the previous slide. So we have some ex ante pricing P, and we have some remaining set of items R. The first thing we're going to do is to scale down the prices in P. And what that's going to do is it's going to return some of the revenue of the seller as utility to the buyer. And now the buyer, we can argue that the buyer has sufficiently high utility, even though some of the items they were purchasing before are not available. And then what we do is we scale those prices back up to recover some of that utility as revenue. This trick of scaling prices to convert utility into revenue. This is also something we came up with in that first 2019 paper on by many mechanisms. So it shows up here in a different way, but it's really the same kind of technical approach. Okay. Now let me really quickly in 2 minutes tell you what happens with trying to preserve these ex ante allocations. So, as I mentioned, when we, when some items become unavailable, the buyer's preferences shift, and now the buyer might purchase things we didn't want them to purchase, right? And so what we're going to do is we'll basically handle this by proactively removing, so thinning out our supply so that the buyer does not end up choosing items where we have a very tight supply constraint. And the trouble here is, if we start to remove items, we start to lose revenue. And so we have to balance these two effects. So basically, we prove this OCRS in 2 steps. Our first step is what I described to you before. We ignore the ex ante supply constraint and we just focus on revenue, and we say that, well, we can recover a good fraction of the revenue. But we also make sure that we're not lowering prices by too much. We keep the prices high enough. If we lower the prices, maybe all the revenue is coming from all the over allocation. But if we keep the prices at a reasonable level, then and are still getting good revenue, the allocations might have shifted across items, but altogether we're not over allocating by a lot. Okay, and so that's what I just said. And in fact, we can prove this kind of lemma for an arbitrary subset of items. We don't need this precondition that every item belongs to it with probability 1/2. And this is important because now I'm going to tell you how we thin out the item supply. Okay, so the way we thin out the item supply is we argue that we can look at this remaining set of items And we can pick some distribution over subsets of it. And we can apply our revenue recovery lemma to this subset. And we pick the distribution in such a manner that it continues to recover about the same amount of revenue while fixing the item allocation probabilities. And this loses us some small constant factor, like a 1 minus 1 over E. And I won't describe the technical details, but I want to show you just one cute little lemma that this depends on. It's this lemma that says the following. So we have some vector W that we are interested in recovering. And if I look at any subset of the dimensions, so like this dimension 1, I know that I have a set of vectors, and these correspond to these pricings for subsets of the set R of items. I know that we have these vectors that in L1 norm along those dimensions cover all of W. But W doesn't lie inside the convex hull of these. We show that there's some vector that lies inside the convex hull of these vectors that is long enough comparable to W. And that allows us to recover the revenue. Okay, so this was really quick and maybe didn't make a whole lot of sense, but I'm out of time. So let me just summarize with this set of results. And as I said before, these results are all in comparison to the ex-ante item pricing optimum. And with the loss of another factor of log M, we get this approximation against the ex-ante by many benchmark. And if you're curious about how this compares to previous work on revenue maximization under item independence, because there are lots of little overlaps between these results, I'm happy to describe these offline a little bit. Let me just conclude with a few open questions. So Mihal already asked, what about submodular functions? And I think that's a very interesting question. And I don't know which way it would go. Another question is, for subadditive and XOS buyers, we showed that the gap between sequential item pricings and ex-ante item pricing revenue is logarithmic. The gap between ex-ante item pricing and ex-ante by many is logarithmic. So the overall gap becomes log squared, but we don't know if the log squared is necessary. So maybe there's a way to combine these two arguments and get a single log here. That's another specific question. The pricing we come up with, it's algorithmic and computationally efficient as long as we have the ex-ante solution given to us, the X's and the P's, and we don't know how to get those efficiently. So that's one open question, and it's an open question that also applies to the Zhao work that did this for independent values. And finally, also, it would be nice to be able to have a sequential item pricing that was oblivious to the ordering of the buyers. And this kind of thing you can get sometimes under item independence, and we don't know if we can get in this context. So that's another interesting direction to think about. Okay, and that's it. Thank you.